Good evening everyone. My name is Renu Raman Sahu and today we will be discussing some of the problems from week 7 of the assignment. So let us go to the first question. So the first question is uh, the magnetic vectors are related as, so you have these four options and so how are they related? So let us just try to understand what these vectors are. So uh, So the vector M, it is called magnetization vector, which is uh, magnetization. So if a particular material is kept in a magnetic field, okay, suppose this is a material and it is kept in a magnetic field, uh, then what happens is this. Uh, so there would be certain domains of magnetic dipole moment. Okay, they will try to get a line and so there will be a magnetic moment, a net magnetic moment per unit volume. That is this quantity magnetization. So what is this H? This H is called the magnetizing field. Okay, magnetizing field. So it is, you can think of it as uh, like the amount of circulating current. For example, in a solenoid, you have so you'll have certain number of wires per unit length. So H is N times I, where I is the current. So note one thing is one thing that it is dependent only on the current. Okay, so H is it is kind of a field which we can control experimentally. So yeah, uh, so we have this M. M is the magnetization, which is the magnetic uh, dipole moment per unit volume of the material, and we have this H, which is the magnetizing field, and we have an experimental control over this. Experimental control over this. Okay, and so basically this M, it comes from the internal circulating currents, which is suppose this is a material, and if you look at a very small part of the material, there would be some internally circulating currents or the electrons. So those things that give rise to magnetic moment, or there would be some spins, okay, that will align and give rise to this magnetization M. And this H you can think of it as an external current that you are providing, and and that is creating this field H. And so the effect of this both, how it changes is the effect of this both, they give rise to this net magnetic field. So you can think of it as a kind of free current. Okay, free current, and here these currents are bound currents. Okay, bound currents. So B is the contribution of these two, and what you have is it is mu naught H plus mu naught M. Okay, so this is your relation, mu naught H plus M. So this you can find in any standard textbook in Griffiths or like any standard electromagnetics textbook. Let us now go to the second question. So here what it is asking, the interaction energy of a magnetic moment mu. So this is a magnetic moment in a magnetic field H. It is given by, so the energy can take two value. It is either so it is mu z H. Okay, and mu z is the component of the magnetic moment in the direction of the magnetic field H. Okay, so this is energy. So mu z can be mu times S, where S can be plus minus 1. So that means the magnetic moment, it can be aligned in the direction of this. So mu z can be in the direction of magnetic field or to the opposite of the magnetic field. It can be either of that. So for n spins, the total energy will be what? So total energy will be is equal to energy of spin 1 plus energy of spin 2, so on, energy of spin n. Okay, and each of this is given by minus mu h s1 plus minus mu h s2, so on, minus mu h s n. So this is what it is written over here. So over here this is what it is written, the same expression. So now we have to find the partition function for n non-interacting spins. So note that the spins are non-interacting Zn. So the partition function Zn, it is given by sum over all the energies. Okay, now this is a expression for the energy. Now what are all the possible values of energy? So, and how many values of energy are there? So let us try to understand that. So this S1, it can take plus 1 or minus 1. So this can have two values. This can have plus 1 or minus 1. This can have two values. And similarly, and there are n such term, and n such term has two values. So the number of possible value of energy is 2 to the power. So it has 2 times or 2 values of energy, then 2 values of energy, so on into 2 n times. Okay, so there are 2 to the power n values of energy. So this is the sum over those 2 to the power n values of energy, e to the power minus beta e. So when I say this sum, it means it is e, so e, or I can say ej, and j is equal to 1 to 2 to the power n. Okay, and each of this, so this is what so this is what we have. And now what we are trying to do is, so what we can do now, we can try to put this expression for the energies in here. So we have this expression for energy. So I'll just try to give you a simple yeah. So what we have is, so z is equal to sum over e, where e, there are to the power n values of e to the power minus beta e. Okay, and what is this e? So e to the power minus beta, instead of e we can just write, so it is minus mu h sum over I is equal to 1 to n si. Okay, so this is what the expression of the energy was. And so this is nothing but sum over e to the power minus, so there are two minus, it will become plus, so this is beta mu and sum over I is equal to 1 to n si. Now see the product over, so we have this, right, e to the power x plus y is equal to e to the power x into e to the power y. So the sum over the exponent, it will become a product. So what we will do now is sum over e, and it is product over I equal to 1 to n e to the power beta mu si. Now remember that this e, it has 2 to the power n values. Okay, so e1, e2, e3, so on e to the power a. So e sub, so there are e number of values are e to the power n. This many values of e's are there. Okay, so what we will do now, we'll now try to, so this e represents, so say all these energies. These energies are the sum of all the energies of the individual spins. Now what we will do, now we will bring in this picture that these electrons are non-interacting. So what will happen is, so we can now sum over this Si, keeping, so we can now, what we can do is, this sum will now try to interchange I is equal to, so now what we are going to do, Si is equal to +1 or -1. So sum over Si product I equal to 1 to n e to the power beta, and there is this thing h beta mu h Si. Okay. So because it is non-interacting, we will be getting this. So now what we have is, so now see, uh, so when we are interchanging these two sum, so this sum is now becoming the sum over all the spins, and this is for a fixed value of I, we are summing over the spins. Okay, and since this product is a product over this particular sum, it is taking care of all the all these sums. Okay, now what we will do is, this is product over I equal to 1 to n e to the power, so spin, there are two values of spin, right, +1 and -1. So when we sum over the spin, it will be beta mu h plus e to the power minus beta mu h. Okay, and this will be this, and this is nothing but product over I is equal to 1 to n, this is 2 cos hyperbolic beta mu h. Okay, and since, see, this term is now independent of I, so what we will get is 2 cos hyperbolic beta mu h to the power n. Okay, so one thing you can notice is that this, since it is non-interacting, so because it is non-interacting, now we have, so this, you, if you remember, this is the partition function for a single particle or the single electron. Okay, so what we can just write, z1 to the power n. Okay, so Zn, the partition function for the n non-interacting particles is Z1, or the partition function for a single particle to the power n. Okay, now we are going to use this to find the other relevant quantities. So what the question is asking is, say this, the interaction energy of okay, so we know what Zn is, we just found out that it is Zn, we found out 2 cos hyperbolic beta mu h to the power n, whole to the power n. Now what is f? F, from basic statistical mechanics we know that it is kBt log of Zn. So this is what we have to find. So like if you are following, then you can simply figure out that it is minus kBt log Z1 to the power n. Okay, so this is minus n kBt ln Z1. Okay, and Z1, you know that Z1 equal to 2 cos hyperbolic beta mu h. This is what it is. And so what we have is minus n kBt ln Z1. So which is it? So 2 cos hyperbolic, oh, so here we already have Zn, and so this is your correct answer. Okay, so just for the sake of completeness, we'll write f is equal to minus kBt ln Zn minus kBt ln z to the power Z1 to the power n, and minus n kBt ln Z1 is 2 cos hyperbolic beta mu h. Okay, so this is how you have to solve this question. Now let us come to the third question. So it is asking, assuming r square equal to a naught square. What is a naught square? So a naught square, a naught is the Bohr radius. Okay, Bohr radius, which is 0.529 angstrom. So you have to calculate everything in CGS units. So it is 0.529 into 10 to the power. So 1 angstrom is 10 to the power minus 8 centimeter. Okay. So the diamagnetic molar susceptibility of atomic helium, so that we have to find. So it is so the diamagnetic molar susceptibility, it is given by x, and this particular so usually it is a Larmor diamagnetism. So it is minus z. So this minus sign signifies that it is a diamagnet. Okay, a square over 6 mc square into an a to r square. Okay, so what is z? Z is equal to 2. So z is the number of electrons. Okay, for helium there are 2 protons, so there are 2 electrons. E is the electronic charge. So in electrostatic unit, so because we have to find in CGS unit, right? So that is why we have to use this E in CGS unit. So it is 4.8 into 10 to the power minus 10 electrostatic unit. Okay, and you remember that 1 coulomb is equal to 3 into 10 to the power 9 electrostatic unit. So this is the conversion, okay, that you can remember. And m is, so we know it is mass of the electron, it is 9.1 into 10 to the power minus 31 kg, but we have to use in gram. 9.1 into 10 to the power minus 27 gram. Okay, and then c is the speed of light, so 3 into 10 to the power 10 centimeter per second. This is centimeter per second. C, and A is the Avogadro's number, 6.023 into 10, 6.022 into 10 to the power 23 per mole. So this many atoms per mole. And R we just have to take it as Bohr radius, A naught, which is 0.529 into 10 to the power minus 8 centimeter. So when you put all of this on substituting these values, you will get x, the diamagnetic susceptibility, it will come out to be minus 1.58 into 10 to the power minus 6 centimeter cube per. Okay, so this is how you solve this question. And let us go to the next question now. So here we have to find a pair of ions which have G is equal to 0 but L and S not equal to 0. So what it tells you is, so how do you approach this problem is by using something called Hund's rule. So I will just tell you how these Hund's rules are applied. Okay, and so I will just tell you the algorithm how it is applied. For example, we have, so let us first look at this one. So Mn3 plus, okay. So manganese, it has a Z of 25. So if you look at its electronic structure, so manganese Z equal to 25. So its electronic configuration can be written as the argon core 4s2 and 3d5. Okay, and manganese 3 plus means we have to remove 3 electrons from it. So the way we remove electron is, first you go to the outermost cell, which is the 4th cell, you take the 2 electrons, then you go to the next inner cell and take out one electron. So that is how you get 3 Mn plus 3. So Mn plus 3 will have electronic configuration argon and 4s0 and 3d4. Now remember that, so D has L value of, for example, S, P, D. So S has 0, P has 1 and D has 2, SPD. So D has L value of 2. So ML values will be for D orbital, so -2, -1, 0, 1, 2. Now you have to fill 4 electrons in these orbitals. So the way you do is you start from the extreme left, 1, 2, 3, 4. This is how you fill the electrons in these orbitals. Then you find L, S and J. So how do we find L? L is the sum over all these ML values and the magnitude of that. Okay. So sum over all the L is 1 plus 0 plus -1 plus -2, and so it is -2, and we have to take the mod of that. So it is 2, the magnitude of that. So we are just summing -2 -1 plus 0 plus 1 and taking the magnitude. The value of spin will be, so this is spin half into 4. So it is spin will be 2. Now note that this electronic configuration is less than half filled. So according to Hund's rule, if it is less than half filled, we have to take L minus S mod for J. Okay, so it will be J equal to 0. So now you can immediately see that so Mn3 plus, it satisfies J is equal to 0 and L is equal to S, and L and S are both not 0. So Mn3 plus satisfies this criteria. Okay, so and this is the only place where Mn3 plus is there, so this would be the correct answer. But we'll try to see why chromium 2 plus is also correct answer. So if you look at, so the point here is that it is the d4 orbital. So if you have the orbital as d4, then you will get this kind of configuration. Okay, so let us see what is that of chromium 2 plus. So chromium has, you see, Z equal to 24. Okay, so it is argon 4s2 and 3d4. Now chromium 2 plus will have, we have to remove 2 electrons. So it is argon 4s0. Okay, so we have removed these 2 electrons and 3d4. Now see, it has d4 configuration again. The electronic configuration of these two are the same. So that is why here also the same calculation will apply, and you will get L equal to 2, S equal to 2 and J equal to 0. Okay, because of the same reasons why we got these values. So because of the similar configuration, we will get same L and J, and see here L is equal to S. So L is equal to S, which is equal to 2, and J is equal to 0, and L and S are both not equal to 0. So your correct answer is this. I hope you understood this question, how to solve this. Okay. Now let us go to the next question. The ground state terms for dy3 plus and okay, so we will do this question. So let us start with this. We have to find the ground state terms. So the ground state terms are, so from this so the approach to solve this problem is, you have to look at what is in the outermost cell, or valency electronic configuration. So for this outermost electronic configuration, you have to find what is S, what is L and what is J by applying Hund's rule. Then what we have to do, then from this, then we write the term symbol as 2s plus 1 L J. Okay, And L, so for different orbitals, so S means L equal to 0, P means L equal to 1, D means 2, S, P, D, F, G, H, so this will have L equal to 3, 4, 5 and so on. So for these values of L, we'll replace it by this corresponding letters, and we'll write J from here. So these are those terms. Okay. So these are called term symbol. Term symbols. Okay. Now let us try to work out an example for dy3 plus. So the electronic configuration is already given. dy plus 3, it has xenon. Xenon is the electronic configuration of xenon. It is a very stable thing. All the cells are completely filled with electrons, so we don't have to worry about that. So 4f9, 5s2. So s orbitals can have at max 2 electrons. So so this 5s orbital is totally filled, and 5p6. The p orbital can have a total of 6 electrons, and it is also filled. So now what we are going to do, so this is 4f9, which so this f9 orbital is that is creating the magnetic field, if there is any, or that will contribute to this term symbol. So when we talk about f, so the L value for f is 3. Okay, for f orbitals, this L value is 3. So ml values will change from -3, -2, -1, 0, 1, 2 and 3. Okay, and we have 9 electrons. So 1, 2, 3, 4, 5, 6, 7. Then we fill. Oh, okay, so these are 7, 7, 8, 9, 8 and 9. So this is how you fill all the orbitals. So from here, how do we get the L? So it is -3 plus 3, -3 2 times. So -3 and -2 2 times, because there are 2 electrons here. -1 1 time, plus 0, plus 1, plus 2, plus 3. So this will give me, so sum over, so basically L we find like this. Okay, so it is -3, -3, -2, -2, because there are 2 electrons, -1, plus 0, plus 1, plus 2, plus 3. Okay, so this 3 cancels this 3, this 2 cancels this 2, -1 cancels -1, and we are left with, I have to take the mod of that. So this would give me 5. Okay, and what is S? S is the total spin. The total spin, so this is plus half minus half, this will give me 0, plus half minus half, this will give me 0, this is plus half plus half plus half, so 5 times plus half, so it is 5 by 2. Now note that this thing is more than half filled. The cell is more than half filled. Okay, so J will be equal to L plus S magnitude of that. Okay, and L plus S is 5 plus 5 by 2, it is 15 by 2. Okay, and L, what will be the value of L? Note that here L is how much? L we got as 5. Okay, since L is 5, L equal to 5 corresponds to H. So the term symbol will be, so L, 2s plus 1 is how much? 2s plus 1 will be 6, because, so I'll just write, this implies 2s plus 1 equal to 6. So here, and J is equal to 15 by 2. So what we have now is 2s plus 1 will be 6, J is equal to 15 by 2. So this is the term symbol, And from here we see that this is dy plus 3 already have. So this dy plus 3, this the first option is this one. So this should be your correct answer. But now, but let us see what will be the term symbol for these values also. Okay, the titanium 3 plus. Let us try to work out this titanium 3 plus and this as well. Okay, and this lutetium 3 plus. Okay. You're understanding how these are calculated, right? I hope it is clear to you. Okay, so now we'll do titanium 3 plus. So titanium 3 plus, it is given by, so the uh, electronic configuration of titanium 3 plus, it is titanium 3 plus, it is argon and it is 3d1. Okay, and the 4s orbitals, they are actually so titanium, it has z is equal to 22. Okay, so it is the actual electronic configuration is 4 argon 4s2 3d2. Okay, and you are removing the 3 electrons, so 2 electrons from here and 1 electron from here you are removed, and you are left with this, and this will be 4s0. So basically d orbital means L equal to so s p d f. So s has L value 0, p has L value 1, d has L value 2. Okay, so ml values will be -2, -1, 0, 1 and 2, and here you have to fill only one so, and then you can find what is s, what is L and what is J. Okay, and since you have only one electron, s equal to 1 by 2, half spin half, L is equal to -2 and the magnitude of that. Okay, and J will be equal to, since it is a half filled configuration, less than half filled configuration, what we can do is so what we have to do is J is equal to L minus S, its magnitude. So this is 2 minus 1 by 2, its magnitude. So 2 minus 1 by 2 is 3 by 2. Okay, so L we got here 2. 2s plus 1 will be how much? 2s plus 1 will be 2. Okay, because it is 2 into half plus 1, which is equal to 2. So the term symbol will be 2s plus 1 L J. J we have 3 by 2. So let us find L. So S P D F. So S is 0, P is 1, 2. So this is for the value of L. Okay, and this is 3. You see, L equal to 2, L equal to 2 corresponds to D. So it is D, 2s plus 1 is 2, and J is 3 by 2. J is 3 by 2. So this is your term symbol for so this is your term symbol for titanium 3 plus. Okay, so that is what you see here, 2D 3 by 2. Okay, now let us look for this xenon. Xenon has so keep in mind that xenon has F14, 4F14, which is totally filled. So a totally filled orbital will have s equal to 0 as well as L equal to 0. So let us try to do this. Lutetium 3 plus has xenon 4F14 and 3s3 5s 5p. So if you do that, so it has xenon and 4F14, 5S2, 5P6. This 4F14, so F means S, P, D, F, so 0, 1, 2, 3. So ml values will be -3, -2, -1, 0, 1, 2, 3. And you have to fill 14 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. So S will be, see, all are plus of minus of, so it will be 0. L, see, -3, -3, -2, -2, -1, -1, 0, 1, 1, 2, 2, 3, 3. So if you sum over all that, it will be 0. And it is, so more than half filled, so it should be J is equal to L plus S. But since both are 0, J will also be 0. Now, for L is equal to 0, the term symbol will have, so L equal to 0 corresponds to S orbital. So if you want to write 2s plus 1, so this small s refers to, so this s refers to the spin, okay, and it which is 0. So 2s plus 1 is equal to 1 basically. 2s plus 1 is equal to 1. So it is 2s plus 1 L J, it corresponds to 1, L corresponds to S orbital, and J is 0. Okay, so that is the option that you have here. Okay, so this is your answer. This is how you have to solve this question. Okay, now we have to calculate something called Landé G factor. So you know how, so in the previous question we saw how we can find S, L and J from Hund's rule. Okay, now we can similarly find G, because here the only thing that you need to know is S, L and J. Okay, so you can simply, like for example, dy plus 3, what you have, we have S, we calculated S, L and J. So for dy plus 3, what we had was S we calculated 5 by 2, L we calculated 5, and this was more than half filled, so we will have, it is 15 by 2. So it is L plus S, because it was more than half filled. And since we know this, from here we will get G is equal to 3 by 2 plus S into S plus 1 minus L into L plus 1 over 2 J plus 1. This you can simply use a calculator and find it out. So this G value you will get how much? 4 by 3. If you put everything in, you will get 4 by 3. Okay, for dy 3 plus. For titanium 3 plus, we calculated S is equal to half, L is equal to 2 and J is equal to 3 by 2. Now you put everything in this formula and you will get G is equal to 4 by 5. Okay, and similarly for lutetium 3 plus, S we found 0, L we found 0 and J also we found 0. So but G will be equal to how much now? So S is 0, L is 0, so we'll take G is equal to only this 3 by 2. Okay, so your options, the correct answer is 4 by 3, 4 by 5 and 3 by 2. 4/3. So it is the last option, which is your answer. Now let us go to the next question. Here it is again asking about the effective Bohr magneton numbers, which is given by P, and what is that effective Bohr magneton numbers for the ions given in question 5. So and it has already given you. So what is the input that you need? So input is you need G. G you calculated in the previous question, and what you found was G is equal to 3/2 plus S into S plus 1 minus L into L plus 1 over 2J J plus 1. Okay, this is how you found J. So for different ions you can find what is S, L and J, right? And since you know this J, so P you can find very easily G, J, J plus 1. So everything this will follow from the Hund's rule. You should know how to apply this Hund's rule. Okay. Now since we have calculated already in the previous question, so we will not go through this. It is the same thing only. You just have to put the formula, use this formula and get the answer. Okay, and what you will get is that yeah, so you can you use this in your calculator or something, calculator or write a program, whatever, you can get the answer of this. So we can go through some of the values very quickly. That for example, we found J equal to 0 for lutetium 3 plus, Lu 3 plus, right? Lu 3 plus. So since J is equal to 0, we can quickly say that the last option has to be 0. So if J is equal to 0, P is equal to 0. So the last option, lutetium plus 3, it had J equal to 0. That is why P will also be 0. So these two options you are left with. And then if you calculate the first one, for the first one it is dy plus 3. We had found that S equal to 5/2, L is equal to 5, L is equal to 5, and J is equal to 15/2, and from there you will get G is equal to, by using that formula, it comes out to be 4/3, and from there P will turn out to be, P is nothing but J into J plus 1 and square root of that, so this will be 10.65. Okay, so this is your correct answer. Now let us go to the next question. So here it is giving manganese which has 25, whose atomic number is 25, that means it has 25 electrons, and the temperature is given. So let us see what the question is asking. So its electronic configuration we know, the temperature we know, pressure we know. You can consider this vapor to be an ideal gas. Okay, and the paramagnetic contribution to the molar Curie susceptibility at 2000 is how much? Okay, and it has given some data, like for example the Landé G factor you found in the previous question, mu b and kb it is given. So we have to know what is the paramagnetic contribution to the molar Curie susceptibility. So this chi molar, the molar Curie susceptibility, it is given by the Avogadro's number, because it is molar, and G mu b whole square and J plus 1 over kbt over 3 kbt. Okay, now let us see what so what are the things that we have. We know what is mu b, the Bohr magneton, it is already given. Kb is the Boltzmann constant, which is also already given. Okay, the Boltzmann constant is given. the Bohr magneton is given. J value we have to calculate using Hund's rule. Hund's rule. Temperature is given. Temperature is how much? Temperature is uh, temperature is 2000 Kelvin. This is 2000 Kelvin, and Na is the Avogadro's number. Na Avogadro number we know it is 6.022 into 10 to the power 23 per mole. Okay. All we need to find is G and J. Okay. So G also will come from Hund's law. Okay. So since everything is given, so let us try to find what is G and J for this particular term. So what we have is Mn Z25, right? So it will have argon, the electronic configuration will be argon 4s2 and 3d5. Okay, now what we are going to do, so this is a d orbital. D orbital means L is equal to 2, so ml values will be -2, -1, 0, 1, 2. These are ml values, and we have to fill in 5 electrons. So 1, 2, 3, 4, 5. So basically S is equal to 5/2, L is equal to 0, J is equal to 5/2. Okay. Now from here we can find what is the value of G. G is equal to 3/2 plus S plus 1 minus L plus 1 divided by 2 J plus 1. So this is nothing but, say L is equal to 0 and S and J are same. So it is 3/2 plus 1/2. It is 4/2 is equal to 2. Okay, so the value of G is 2 and J is 5/2, and rest all values you know. So you can just put everything and you will arrive at the answer. And the answer that we will get is this one. So the answer after using this value, so this value and G is equal to 2, what you get is chi molar, and the value turn out to be 2.17 into 10 to the power -3 centimeter cube per mole. So this is your correct answer, the third option. I hope this is clear. Now let us go to the next question. So for higher values of temperature, the susceptibility of paramagnetic substances is proportional to. So whenever we talk about a paramagnet, it is always like C goes as 1/T. The susceptibility, okay, of paramagnet goes as 1/T. So this is your, so this is the known Curie law. So this is it will follow a 1/T behavior. Okay, so now we have a question in which the ground state 1s of the hydrogen atom is given and A is the Bohr radius. So what we have to calculate the diamagnetic molar susceptibility, chi molar, for this atom. So let us try to do that. Chi molar. So we have encountered this particular formula before as well. So Z is square and A over 6 mc square and r square. Okay, here Z is equal to 1 because it is a hydrogen atom, and E is equal to 4.8 into 10 to the power -10 electrostatic unit, and M is equal to 9.1 into 10 to the power -27 gram. and c is equal to 3 into 10 to the power 10 centimeter per second, and Na is you know that it is an Avogadro number. Na equal to Avogadro's. So now we just have to find what is this r square. Okay, so uh, how do you find r square? To find r square, all you need to do is this. So r square is equal to the wave function. Take the conjugate of wave function, then so this is vector r square and psi of r and d cube r. Okay, this psi star, it represents the conjugate, and this is our all space. Okay, now let us, we have been given psi and psi star. Since psi is a real function, psi and psi star will be the same. Okay, and now we'll try to integrate this over the entire space. So look here, once we put this r square value, we will have the answer, because rest of the constants that we know. So let us try to find all the find the average r square value. So we have been given that psi of r, it has only a radial dependence, so it is pi a cube, we have to take its square root, and a to the power minus r over a. Okay, so r square now will be is equal to d cube r psi star r, and the function r square and psi of r and d cube r. Okay, now how to, so since it is integral over all the space, so this d cube r we can write as 4 pi r square dr, and we'll try to limit this is 0 to infinity. Okay, and psi of r, it will be pi a cube, and psi of r square psi of r. Okay, so now we'll substitute the expression for psi of r. So this is 4 pi 0 to infinity r square dr 1 by sorry, this is 1 over pi a cube e to the power minus r by a into r square e to the power minus r by a over pi a cube into that's all we have. So what we have is, if you just simplify, it will be 4 pi over pi a cube and integral 0 to infinity and 0 to infinity e to the power minus 2r by a, and this is r to the power 4 dr. Okay, and we let us now dimension make this integral dimensionless. So what we will do, so this is 2r by a, right? So 2 by a to the power 5 and a by 2 to the power 5. We just multiply and divide this a by 2. So what we have now is equal to 4 by a cube, and this is a by 2 to the power 5 and 0 to infinity, and it will be 0 to infinity this is x to the power, so e to the power minus x, x to the power 4 dx. Okay, where x is equal to 2r by a. So this is nothing but a square over 8. And this function is a special function called gamma function. So gamma function is defined as, so gamma of n, it is defined as e to the power minus t to the power n minus 1. So this can be any polynomial, t and 0 to infinity. Okay, so that is gamma n, and gamma n is equal to n minus 1 factorial. Okay, so this will be 4 factorial, and 4 factorial is 4 into 3 into 2, so 4 so this is a square 4 into 3 into 2 over 8. So this 4 2 cancels this, and we are remaining with 3a square. Okay, so this 3a square we have to replace it. So r square is nothing but 3a square. And a will have certain value, that a will have this value of Bohr's radius 0.529 into 10 to the power minus 31 kg. It 0.529 angstrom, or that will give me, so this is what you have to put in a, and you have to convert this angstrom to centimeter or whatever the unit it is asking you. And what you get finally is so what you get finally is chi molar is equal to minus z b square over 6 mc square, and this is r square, and this r square minus z b square over 6 mc square r square equal to 3a square. ठीक है. Now we will put z equal to 1, e equal to 4.8 into 10 to the power minus 10 electrostatic unit, e, then m equal to 9.1 into 10 to the power minus 27 gram, c equal to 3 e 10, and na equal to, this is centimeter per second, and na is equal to 6.023 into 10 to the power 23, and r and a is equal to 0.529 into 10 to the power 8 centimeter. So you just put everything and you will get chi molar is equal to minus 0.237 into 10 to the power minus 6. So that is your answer. Find the expectation. So your correct answer will be the last option. Okay, now let us go to, so this is how you solve this assignments. I hope it is clear till now. Let us go to the next session, so the next set of questions of previous year. So the first question, it is asking the density of states and the Pauli paramagnetic susceptibility for a free electron gas in terms of Fermi energy. So a free electron gas, we know that the density of states is given as, so this we have done many times, even the derivation in the previous sessions. So the density of states so let me just go through how we find the density of states. So the density of states, so if n is the number of states, the density of states is defined uh, like this: dn de. Okay, this integral is over all the energies. It's 0 to infinity. Okay. This is the usually the integral form of definition of density of states, or you can in the differential form what you can do is uh, you have to take the derivative. So n will be a function of energy, and you have to take derivative with respect to E. So we want this GE, right? So that you can do by taking the derivative of n with respect to E. E, and there is this 1 by V. Okay, this is your density of states, expression for density of states. With this in mind, let us try to find what is the density of states again. So n is equal to V over 2 pi whole cube, because it is a 3-dimensional one. This 2, it comes from the spin, and you have to integrate over all the k less than the Fermi. So this k is all the k which is less than certain. So it is which is within a certain radius in k space. This less than k, and this is d cube k. Okay, this d cube k, it can be written as, so I'm just writing here, n is equal to 2b by 2 pi whole cube, and d cube k can be written as 0 to infinity or 0 to k 4 pi k square dk. Okay, and this is 2v over 2 pi whole cube, and this is 4 pi k cube by 3. So what we have now is so we want density of states. So okay, so we have this k. Now we can use a dispersion relation. A is equal to h bar square k square over 2m. So from here we'll get k is equal to 2me over h bar square and square root of that. So what we can do is just write 2b over 2 pi whole cube, and this is 4 pi by 3, and instead of k you write 2me over h bar square to the power 1 by 2, and it has a power of 3, so it is 3 by 2. Okay, now you just put everything in this formula, use this expression. You just have to take a derivative with respect to the energy, and on simplification you will get g of E using that formula. It is 1 by 2 pi square and 2m over h bar square 3 by 2 to the power 3 by 2, and square root of EF to the power 1 by 2. So this is the density of states of free electron gas at in terms of the Fermi energy. So which is it? So this option looks correct to me, and this is also correct, and these are not correct because there is no square root E dependence. Yeah, this is fine. Now the polyparamagnetism, it is given as it is given as mu b whole square. Mu b is the Bohr magneton times the density of states at the Fermi level. So we know what is mu b is. Mu b is just the Bohr magneton. We know that mu b is equal to 9.27 into 10 to the power minus 24. Yeah, in assignment. Okay. Now what we will require is g of EF. We have just 100. It is 2 pi square and 2 over h bar square 3 by 2 and square root of EF. So this is your Chi Pauli. and the option which matches with this is your correct answer. So it is just g of f times a mu b square multiplied to it. So which looks like this is the correct option because it has ef to the power half dependent, it doesn't have. So the correct answer is this one. Now let us go to the next question. So the number of atoms per unit volume of iron crystal is this much. This is number of atoms per unit volume is given. Number of atoms per unit volume. It is given as n is equal to 8.5 into 10 to the power 28 meter cube. Now these are the number of atoms, right? And let us see each of these atom will have a magnetic moment. Each atom has a magnetic moment mu naught is equal to 2.2 mu b. Okay, mu b is, and mu b is nothing but 9.27 into 10 to the power minus 24 joule per Tesla. Now what we will do, we want to find the magnetic moment per unit volume of iron crystal. So magnetic moment per unit volume, it will be given by so it will be given by mu naught. It is the single magnetic moment and the number of electrons per unit volume. Okay, so this thing is given as 2.2 mu b, and n is so n is the value which is given in the question. So what we will have is the magnetization amp. It is given as 2.2, mu b is 9.7. Sorry. 9.27 into 10 to the power minus 24, and n is 8.5 into 10 to the power 28. So this thing will give me, on calculating this, will get 1.75 into 10 to the power 6. So somewhere around this value will get, and so this is so it will give me 10 to the power 6 in ampere per meter. So your correct answer is 1.75. So it is just put the formula, get the answer. So which of the followings are magnetically ordered state? So a magnetic ordered state is that in which there is some level of periodicity or a repetition of the spins or the magnetic dipole moments. So here we can see clearly that so this is a long range order, this also has a long range order, and this also has a long range order. And here it is not, so it is not ordered here. Why? Because each one of these is pointing in some random directions. Okay, so that resembles that there is no order here. But here you see there are repeating units of the so the unit cell is getting repeated. Similarly, in the case of antiferromagnet and the ferrimagnet. So your correct answer is this one. The magnetically ordered states are the ferromagnet, antiferromagnet, and the ferrimagnet only, not the permanent. Now it is asking the correct spatial part of the total wave function for two electrons having spin part. Okay, so the total wave function psi is the wave function. It is given as psi of spin into spine of spatial part. Okay, and this overall thing, the requirement is that since we are talking about the electrons and electronic system, we have to remember that electrons are fermions, and since they are fermions, they will obey something called the Pauli exclusion principle. And now, if one is symmetric, the other has to be antisymmetric. Now you see here, psi spin, it is given as 1 by square root of 2 up down. So you don't have any distinction between up and down in this particular state, plus down up. This is also totally symmetric. Okay, since these are symmetric, so this is the typical case of a symmetric case. Symmetric, or to be more particular, it is a triplet state. Okay, triplet state in which the total spin is 0 and the z component of the spin is also 0. So it is a symmetric state, and since it is symmetric, the spatial part has to be antisymmetric. So now let us come to the spatial part. Psi of spatial part, it should be such that on interchanging R1 and R2, you will get so if you interchange R1 and R2, you will get a negative sign. You will get the negative of this wave function, and if you put and this wave function has to be normalized. Okay, so it will be like psi A R1, psi B R2 minus, now we have to interchange R1 and R2, psi A R2, psi B R1. So this is the form of the wave function of the spatial part. Now we need to have this normalized. So if you assume that this psi A, psi B, psi A R1, R2 and psi A, psi B R1, these all are normalized, then it is just, you just have to multiply a prefactor of square root of 2. Okay, and the product of this wave function, the spatial part of the wave function and the spin part of the wave function, will give rise to that will give rise to the wave function, and yeah, so that will give rise to this antisymmetric wave function. So your correct answer will be something like this, 1 by square root. So this looks like your answer. This 1 by 2, why it is not? Because this is not normalized. It is antisymmetric, but it is not normalized. Okay, so now let us go to the next question. So what is the value of total spin and its component along S for the problem specified in the previous question? So the problem specified in the previous question, there we had, so we have to find what is S and what is MS. And the spin configuration was this. So psi spin, it was nothing but 1 by square root of 2 minus इधर से ऊपर उठ रहा है. Okay, so there are so it is a symmetric spin. You see, this is up, down, down, up. This state is called a triplet state. So the spin 2 and here the spin will be 0 because here this up, down, spin up and spin down, it is a 0. It has no spin, it has no spin, and it is a triplet state. So what is this triplet state is that see, two electrons they have individual spin half, and the other also has the spin half. So when they combine, so by this combination of this spin, so it when the spins are added, they can either take this value s1 minus s2 to s1 plus s2. This many values it can take, and s1 minus s2 is 0, s1 plus s2 is 1. Okay, so when you combine these two spins, what you have is this what you have is this these two different total spin states, and j can be 0 and j can be 1. So the uh, so this is your total spin component, total spin, and there would be another component, the z part of the spin component. The z part of the spin component for this will be just 0, and for this it will be minus 1, 0 and 1. Okay. So the electronic configuration for this, it is given by 1 by square root of 2 up down minus down up, like this. So this is a singlet state because there is only one state there. And these three are called triplet state because there are three states, and it is given by up up, it is given by up down plus down up 1 by square root of 2, and this is given by down down sorry, this is plus 1 minus 1. So these are the three states, and this is a triplet state with mj is equal to 0. So yeah, j is equal to, so j is equal to 1 and mj is equal to 0, or this capital S. So okay, it is written as capital S here. Capital S is equal to 1 and ms is equal to 0. So this is your correct answer. Okay, so I hope you understood why how this is done. Now let us go to the next question. So it is asking, what is the value of product S1 dot S2 for the total spin S of two spin half particles? So the total spin S. Hello, do you have some doubt?
Hello. Hello.
Yeah,
Good evening, sir.
yeah,
Good evening, sir.
yeah. Tell me.
Sir, please show again the question number 4. Question number 4, sir.
This one.
4, sir.
This is 4, right?
Right, right, right. Thank you, sir. Thank you, sir.
Okay. So do you have some doubt here or what?
No, 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 sir. No, sir.
Okay. Yeah. Okay. So now let us do this question in which you have to find the value of the product S1 dot S2 for a total spin. So the total spin S is given by this S1 plus S2, and what we need is we have to find this product S1 dot S2. So what we do is we try to square on both sides. So what it basically means is we have to calculate S dot S, which is nothing but that is what we call S square. So it will give me S1 square plus S2 square plus 2S1 dot S2, and we have been given that the total spin S has to be 0. Okay, so this will be 0 is equal to S1 square plus S2 square plus 2S1 dot S2. So we have to find what is this S1 dot S2. So we have to know what is this S1 square and S2 square. See, this S1 square and S2 square are the operators. Okay, and these operators, when for example, how this acts on a particle is, if S, so you have to remember that these are operators, and S square, when it acts on a, let's say, some spin spin half particle. So what it will give me is, it is h bar square uh, half into half plus 1 times uh, so this is your eigen value. Okay, this is what you will get. So when I say uh, so what is the value of the product? This means this is not just an ordinary product. It is an operator. S1 dot S2 is an operator, and uh, say these operators have. So if you operate it on some spin state, it will give me s into s plus 1. So what I will have is, this is half and half plus 1 plus half and half plus 1 plus 2. So I hope you understood from here. This is the key part to understand. Okay, so 2 s1 dot s2, it is an operator. This has to be equal to 0. This means 0 is equal to, this is 3 by 4 plus 3 by 4 plus 2 s1
Okay.
dot s2. This will give me,
Sir,
yeah,
excuse me, sir.
yeah, tell me.
Sir, how S1 and S2 both are the operator, na?
Yeah, yeah, both are operators.
How S1 and S2 both are equal?
Uh,
S1 square and S2
See,
square?
S1 and S2, these are operator, but they operate on the two spin half particles. You see,
Sir,
so the particle
sir,
one
how?
is a spin half particle, and particle two is also a spin half particle. So
Okay.
S1
Okay.
is a spin half particle. So when S1 square will act on this spin half particle, right? And S2
Okay.
square will so this is S2 square will also act on this spin half particle. This is
Sir,
fine.
when both are operates on spin of particle, then S1 square is equal to S2 square operator.
Mm, say the operator operators are equal if their action is equal on some given wave function. Okay, say if
Okay.
s1 square, so what I'm saying is that, so up to this it was operators, right?
Sir,
And if this operator, this s1, if it operates on a spin half particle,
sir,
then it will give me this half half plus 1. So, or how do I say, yeah, this h bar square. Since this eigenvalue is same, so the action of s1 is same as, so I'm not saying that s1 is equal to s2. What I'm saying is, uh, these are different operators, but their action on the spin half particle, it is same.
sir. Okay, sir.
You got it right?
Yes, sir. Yes, sir.
Yeah.
Thank you.
So from here we can just know this s1 dot s2 we can find. This is minus 3 by 4. Okay, so this is your answer. Now let us go to the next question. I hope this calculation is clear to you. So or maybe you can look into some references, addition of angular momentum. Okay,
Yes, sir.
addition of uh, spin angular momentum. You can look that in Griffith chapter 4.
Okay, sir.
Okay, there it has explained nicely how do you get this triplet state, singlet state, and all these calculations that you can find. Okay, so
Okay.
so
Thank you,
that
sir.
would be more useful to you.
Thank you, sir.
Yeah. Okay, so now we will talk about this seventh question. So it is asking, what is the paramagnetic susceptibility of an atomic gas with number density n is given in the ground state. Sorry, some value n is the number density. Temperature T is equal to 400 Kelvin, and the paramagnetic susceptibility is given, chi is equal to 6.0 into 10 to the power minus 11, and the valency electron configuration is F7, and we have to find what is the value of n. Okay, and what it has given is given that the magnetic permeability of free space it is given, Bohr magneton value is given, Boltzmann constant is given, and it has also given the paramagnetic susceptibility. So okay, so paramagnetic susceptibility is given here, and let us see, and we have to find mu naught mu effective whole square and 3 kBT. Let us see this formula carefully. What we have, this chi it is given, it is given here, chi is given, n is what we have to find, and we have to find mu naught it is given, mu naught is given here, and 3 it is a constant, kb it is the Boltzmann constant, kbt, so it is also given, temperature also we know that it is 400 Kelvin. So we have to find what is this mu effective. Mu effective, let us see how do we see this mu effective. For mu effective it has already given the formula, right? So what we do is mu effective, it is G mu b is the Bohr magneton whose value is given already, J into J plus 1. Now all we have to find is what is the value of this J and what is G, right? What is G, and so and what is G also, G also it has given, it has given the formula, not directly, and J it has given. So let us try to find out, let us try to find this out. Okay, and how do we find this G and J? We find it from this electronic configuration. So F7 we have to find the G and J value corresponding to this F7. So for that electronic configuration, let us try to get it. So we have to find corresponding to F7. So now you see S, P, D, F. So L equal to 0. So L is equal to 0, 1, 2, 3. So for F cell, the ML will be what? ML will be minus 3, minus 2, minus 1, 0, 1, 2, 3. And after filling this, you can find S, L, and J. So let us try filling. So we have total 7 electrons here, 7 electrons. So we'll apply the Hund's rule, 1, 2, 3, 4, 5, 6, 7. Okay. So now S will be how much? S will be 7 by 2. L will be, say, sum over all this, minus 3, minus 2, minus 1, 0, 1, 2, 3. So it is L is equal to 0. And J is nothing but, it will be 7 by 2 again. Okay, so J we have 7 by 2, we have S, and we have L. So from here we can calculate G. G is equal to 3 by 2 plus S, S plus 1 minus L, L plus 1 divided by 2 J, J plus 1. Okay. This is what? This is, you just put everything 3 by 2 plus S is 7 by 2 into 9 by 2 minus 0 over 2 into 7 by 2 into 9 by 2. So it is just 3 by 2 plus 1 by 2, which is nothing but 2. So you have G. So now you have mu effective. Mu effective is how much? G root under J, J plus 1 into mu B. So G is 2 and j into j plus 1 is 7 by 2 into 9 by 2 square root under, and mu b is 9.27 into 10 to the power uh, minus 24 ampere per meter square. So you now have this mu effective also. So that is how you calculate this mu effective. So now you have this, you have all these values, and from there you can calculate n. Okay, and I hope this is clear how you will find the.
Yes, sir. Yes, sir.
Okay, fine. Uh, Now let us go to the next question. The commutation relation for spin half system is, so this is a very like well known spin algebra if you read from, like from the same reference only, like Griffith chapter 4 last part. Okay, so there you have this kind of so spin is nothing but so what are this S I alpha, S I beta? So I here this subscript refers to the ith spin. Uh, so spin is nothing but h bar by 2 sigma, where sigma is a Pauli matrix. Okay, so and Pauli matrix means it has sigma x is 0 1 1 0, sigma y is, these are matrices which are uh, 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 like which will give you so if you do the matrix representation of this spin half particles, okay, then you get this type of matrices. So 0 minus I 0 and sigma z is equal to 1 0 0 minus 1. Okay, and the interesting thing about this so these operators is that if you take the commutator means sigma x sigma y minus sigma y sigma x, so it is just matrix multiplication, then what you will find is it is 2I sigma z. Okay, uh, so similarly if you do this sigma y and this is how it is written, sigma x sigma y, this commutator is like this. So sigma y sigma z, this commutator will be 2I sigma x. Okay, and so this, if you do this matrix multiplication, you will get to you will get this easily. So sigma z sigma x commutator will give me 2I sigma y. So you see there are these three relations like three so what you can also do, so let me just again do that. So what you can do now is see all these things. So how you can write this as a single equation? So what you do, sigma I commutator sigma j, where I j okay, this is iota. Okay, you shouldn't have to confuse this I with this I. 2I sum over epsilon I j k sum over k sigma k. So let me just try to evaluate one of this. Okay, so the way we evaluate is uh, so this single equation, this encapsulates all these three equations. Okay, and since s is given by this h bar by 2, you will have this thing. So if you just multiply each of this by h bar by 2 h bar by 2 h bar by 2 all this, so what you will get is this kind of relation. Just a minute. So this is equal to, so let me just try to evaluate this. Sigma x sigma y is equal to 2I sum over k. So k varies from x, y, z. So this is epsilon x, y, k, sigma k. This means 2I epsilon x, y, x, sigma x plus epsilon x, y, y, sigma y plus epsilon x, y, z, sigma z. Okay. Now see, this epsilon has this property that it is an antisymmetric matrix. So antisymmetric in its indices. So if any two of this become equal, then this will vanish. This will go to 0. This will go to 0. And as epsilon x, y, z, it is the value of this is 1. Okay. So what you have is this is 2I sigma z. So similarly, if you just substitute others and apply the properties of this epsilon, so here it has been written alpha, beta, gamma. Okay, alpha, beta, gamma. If you apply the properties of this, you will end up with these three equations. Okay, and the commutation relation for spin half particles. So here I have written for the Pauli matrices, right? For the spin half particle also it is not very spin half particle. What you have to do is just multiply h bar by 2. Or what it has done in this case is it has taken just 1 by 2 sigma. It has taken this h bar as 1. So sometimes we neglect h bar. So if you just take that, so let us not do that. So h bar by 2, h bar by 2, h bar by 2, and h bar by 2. So what we have is this is sx, sy minus sy, sx is equal to uh, so we have to multiply 2 times h bar by 2 because on both sides of this equation we need this. So 2I 1 becomes this and this h bar by 2. So the actual equation is what? The commutation relation Sx Sy. This is nothing but I h bar Sz. Like, do you understand how we got this value? So I hope this is clear. So what we have done is we took this commutation relation of the Pauli matrix and it is clear, right?
Yes, sir.
Yeah. So we have just multiplied this h bar by 2 twice. And what it has done in this question is that it has kept this h bar. There should be an extra h bar here, which it has just kept it. So sometimes in some cases they neglect h bar actually. They put it as 1. So basically the point to note here is that there has to be an iota and there has to sum over this epsilon. Okay. So none of the case has that sum. So this is the correct answer, the commutation relation, correct commutation relation. Okay, and this again you will find in the 4th chapter of Griffiths. Okay, that is the spin is a very important part and its algebra is also very important. So you just go through that. Okay, here it is another interesting question. So what we have to find is, so it has given the Heisenberg Hamiltonian. So Heisenberg Hamiltonian, it is just the interaction between two spin states, two spins, and the total spin is given by this sz total, which is sum over the z component of these two spins, and we have to find what is the commutator of h and sz total. So let us just do that. So it is just a commutator algebra. Okay, so this algebra is also learning. This algebra is really useful. So h s z total. So I'll just go through it step by step. So h is nothing but minus 1 by 2. So I'm just putting it here. J12 S1 dot S2. And sz total it is S1z plus S S2Z. Okay. Now what we have is this is a constant, right? The constant, it can be just taken out of the commutator. So we have to now evaluate just this S1 dot S2 S1Z plus S2Z. Now what we have to do, you see this, let us expand this now. Minus 1 by 2 J12, and we'll have commutator of, so this dot product means what? S1x dot S2x plus S1y dot S2y, this is dot, plus S1z dot S2z, and commutating with S1z plus S2z. This commutator we have to evaluate. So we have now this operator commuting with this operator. So let us, so this will now break down into 4 terms. Minus half J12. So I'll just write explicitly. So first, so this will be, this can be written as commutator of this with this, then this. So how it will be? So S1x S2x commutating with what? S1z, this, plus S1x S2x commutating with S2z. Okay. So this commutated with this, and so these two terms are this. First this, and then with this. Then similarly for the second term we will write. For the second term also we will write plus S1y S2y S1z commutator of that, plus S1y S2y commutator with S2z, plus S1z S2z S1z plus S1z S2z S2z. Okay. Now let us evaluate. So another operator algebra rule that you should remember to evaluate this is that suppose if A, B, C, this commutator you are trying to evaluate, and this A and B are, so this commutator. So this is given by A, B commutator C plus, so this is on the left, so it went to the left, then A, C and this commutator operating with B. So this you can remember, okay, this is an important one, and this you can prove also, okay, that so this thing you can try to see how it happens. So this is, so now that is what we will try to use. Now let us try to evaluate all of this. So this one, this is what, see S1 and S2, this will commute, always commute, okay. S1 any operator will commute with S2 any operator. S1 x y, this will be always 0, or so if these two operators are acting on different particles, they will always be 0, okay. So what we have is, from here the only non-zero term that we'll have is S1x S1z, and you see this S2x is on the right hand side of this, right? So we'll take it to the right hand side, S2x. So it is like, so if we evaluate this and use this one, so we are applying actually this formula here, okay, and like you got this right, how I got this one, and this will be, so in the previous question we evaluated that it is uh, I epsilon, so this is x z, right? So x z y s y s 2 x, okay. And this x z y, see this epsilon x z y, it has the property that if this x z y are in cyclic manner, then it will be plus 1, and if it is anti-cyclic, so if it is deviating from that cyclic, so see if it were x y z, then it would have been plus 1, but since it is not, so it is minus I s y. Sorry, yeah, sorry. Okay, so this is what you will get from this term, okay, minus I s. Similarly you can evaluate this one, so s1x, so the s1x is on the left hand side, and this s1x will not commute with s2, this will commute with s2, so you can take it out, and what you have is s2x and s2z, so this thing will give you what, the thing, I, so this is again minus y s1x s2y, okay. Similarly you see from here, what you get here is this, the first term will give you so if you just evaluate it, you will get I s1x s2y plus I s1y s2y, sorry, so s1y came away, and s2x x2x, and from here what you get is, see here it is z and z, so since these two indices are same, so s2z will come out, and s1z commutator, it will give you 0. So you have these four terms, right? These four terms I will just highlight. So this term, this term, this term, and this term. Now you see carefully, this is minus I s1y s2x, and this 2 will cancel each other, and these 2 will cancel each other, okay. So overall what we will get is, this is minus plus, so what you get is overall this total summation, that will become 0. So this commutator, that will be 0. Like I hope this is clear. What you have to do is, you just have to go through this algebra, and you have to use this formula over here, then you will easily see why it should be 0, okay. Now let us go to the last question. So the correct expression for heat capacity at a temperature T for n magnetic moments in a magnetic field H along the z direction. So now what it is asking is, so we have to find the heat capacity, right, for n heat capacity for n of this particles. And so let us find that. So since so we have to first find the partition function. The partition function will be given by, so z is equal to, so let us find for the one particle. For one particle it will be or for the one magnetic moment it will be uh, along the z direction, where each moment having interaction energies mu b h and minus mu b h. So e to the power beta mu b h plus e to the power minus beta mu b h. So beta is equal to 1 by k beta. So this is nothing but 2 cos hyperbolic beta mu b h. It is like this. Now what we need is for there are n magnetic moments in a magnetic field. Okay, so what we will need is Zn is equal to Z1 to the power n. Okay, uh, so so now we can find what is the energy of the average energy. So once you know the partition function, then from statistical mechanics you know that it is minus 2 by dou beta of log of z or Zn. So it is, so this will be 2 cos hyperbolic beta mu b h to the power n. Sorry, to the power n. So this thing will be minus 2 by 2 beta of ln z to the power n. So now it is, let us try to do that. So what we have is so since it is log, so it is minus n rho by dou beta of ln, it is 2 cos hyperbolic beta mu b h. So and this will be now minus n. We have to do this derivative with respect to beta, so it will be cos hyperbolic beta mu b h, and it is 2 sin hyperbolic beta mu b h, then derivative of beta, so it is mu b h, so it is nothing but minus n mu b h tan hyperbolic beta mu b h. This is your total energy. Okay, and beta, you remember beta is equal to 1 by k beta. So its derivative is derivative with respect to temperature is minus 1 by kb t square. Okay, so that we have to do use here. Now C is equal to, so this is average energy rho by 2 temperature, derivative of energy with respect to temperature. So that will be given by minus n mu b h. Now derivative of tan is sec hyperbolic, sec square hyperbolic beta mu b h and derivative of beta is again mu b h, and derivative of beta with respect to temperature is minus 1 by kb t square. Okay, just the chain rule. So if you just do that, what you get is, so this will cancel this minus, and what you have is n times, say, mu b h, and what you can do is again multiply and divide by kb, so that you have this kb and kb, you have it here. Then you can have mu b h over kb t whole square, and sec hyperbolic square beta mu b h. Okay, so this is your expression for the heat capacity. So I think mu b h square, and this is not, so n kb has to be there, n kb is there, and the square of this, so this is your correct answer. Okay, so this is how you solve this question. They are just application of statistical mechanics. I hope this is clear. So we are done with all the questions for today. So if you have to see some previous video or something, you can visit this link. Do you have any questions for today's session?
No, sir. No, sir. Thank you.
Okay, then we can end the session here. Thank you for joining.
Yes. Thank you. Thank you, sir.